Hello, thank you for coming. We're very happy to have today with us a regular of the seminar, Natan Rubin from Ben-Gurion University, and he'll tell us about his recent results about semi-algebraic hypergraphs.
Hello, Adam. Thank you for introducing me and for you all coming here on this very cold winter day. And the center of the talk will be semi-algebraic sets and semi-algebraic hypergraphs. How much time have we got?
55 minutes
Okay,
usually.
so now.
Something like that.
So let's begin with the basics. A semi-algebraic set is such a set in the Euclidean D-space that can be, which is a locus of points which satisfy a certain Boolean combination of polynomial equalities and inequalities. We could assume that all of them are weak inequalities. No loss of generality. So if you look at it closer, each of these polynomials which we use in the inequalities, it determines a certain hypersurface, which is the zero surface of that polynomial. So no matter what is the Boolean combination, we are always looking at a certain combination of features in the arrangement of these zero surfaces. And we say that a semi-algebraic set has description complexity at most delta and s if one can attain such a description as above with the polynomials whose degree is bounded by delta and whose number, the number of these polynomials, is at most s. As it happens, the vast majority of problems in combinatorial and computational geometry deal with semi-algebraic objects of bounded description complexity. For any purpose, it's basically anything except for, say, convex sets or Jordan curves and such. But in general, anything that is nicely shaped, like lines, hyperplanes, balls, half spaces, simplices, whatever, it's always semi-algebraic of bounded description complexity. And those who are a bit familiar with computational geometry and with the notion of duality, we can always map such semi-algebraic sets to points in a certain higher dimensional but fixed dimensional Euclidean space as a rule, excluding maybe some peculiarities, but basically you can describe you can take all the coefficients of the semi-algebraic of the polynomial constraints, and you can pack it all and send it up to some higher dimensional Euclidean space. So it's not surprising that relations between such semi-algebraic sets are described by the means of semi-algebraic hypergraphs, which I'm going to define shortly. For the time being, it's more convenient to work in the k-partite setting. So we are, let us first look at k-partite, k-uniform hypergraphs. their vertices, for the sake of this definition, live in some Euclidean D space. And we seek to describe the subset of all the edges. And of course, each of these hyperedges is a k-tuple of vertices, and we want to know which of these k-tuples are in and which of them are out. And by the way, it's not very important that some points can belong to several of the sets, especially in the k-partite setting. So the way to do it is basically to look at the Cartesian product of these sets, and this Cartesian product lives in dimension k times d, and we take some semi-algebraic set, and we for our hyperedges are going to be the exact k-tuples which fall into this semi-algebraic set. And it's important to emphasize that it actually lives in dimension d times k. And of course, you may ask, okay, what if it's not k-partite? So basically, it's not of course, you want to ask what happens, maybe the order of the k-tuples matters, but for the sake of this talk, whatever we do, it also applies even to oriented k-uniform hypergraphs. So you can say that our sets are symmetric, and anything like this, but it's immaterial for all the results. You can actually fix the order as you like. So we are going to talk of general hypergraphs. The first, it has been discovered that quite since 2005, that semi-algebraic graphs and hypergraphs possess certain very nice, very smooth combinatorial properties. For example, Alon, Pak, Pinchasi, Radushich, and Sharir, I hope I haven't missed anyone. Did I? Is Radosh watching it? Anyhow, they first discovered that if your semi-algebraic hypergraph contains a constant, say, an epsilon fraction of all the k-tuples, then it must contain a really huge biclick. They first dealt with only with graphs, uniformity 2. So provided that epsilon is constant, you can have biclick with sides that are linear. This is an extremely strong property. And it was subsequently extended in a series of papers by Fox, Gromov, Laforgue, Knorr, and Bach, and later refined by Fox, Bach, and Suk, and myself. And so the result, the end result, you can see on the board. Basically, you it was first shown that the size of this bicyclic is polynomial in this coefficient is polynomial in epsilon, and but it depended on the degree, and then it was further improved by myself, as you can see, because it happens that the sort of result is quite useful for a number of basic problems, such as selection in simplicial hypergraphs and k-sets in dimension 5 and higher. And one cannot pass without mentioning all the Zarankiewicz type problems, which have been extensively studied, and I direct you to look into a recent survey by my colleague Shahar Smorodinsky from Ben-Gurion University. If you if you are looking at semi-algebraic hypergraph on bounded description complexity, and you forbid the set and peak size k partite complete hypergraph t by t by t by t, like that, then you can have this bound on the number of edges, and it was actually attained by Fox, Bach, Schaeffer, Suk, and Saal around 2000, I think, 16, depending by conference versions, journal version, and it was, but it was done with a certain arbitrary small constant in the exponent, and the constant was recently shaped over by Tudor.
In your bound, you don't have delta anymore, so it doesn't matter. In your
Well, look, my bound is for the density version. It's true that this problem, the density version and the Zarankiewicz formulation, they are obviously related, but and actually there is, if you look at my more recent version, there is also a similarity between the proofs, at least if you are looking at the older version, which also used Hausler, Pack, and Lemma and such. But so there is a certain obvious connection. So you say if you either have a large sub k complete partite complete hypergraph, or you have many edges, and you are looking at various regimes, but notice in the Zarankiewicz version, except for at least until for most people care less about how t affects the bound, while in density it matters. So suppose we are given a certain semi-algebraic relation, and we have a k-tuple of sets. We say, suppose this relation, so we say that this k-tuple is homogeneous if either all the Cartesian product falls within the relation, it falls into the H set, if you are looking at a subset of vertices within the hypergraph, or if it is the opposite, that it lies completely outside. So if we are looking at a semi-algebraic hypergraph, we say that, let us say that, and first of all, we are looking at the equipartitions in all regularity results, at least in the classical formulations, we are looking at equipartitions. So each parse cardinalities differ by at most one. And we say that such an equipartition is epsilon regular if all but an epsilon fraction of the k tuples of the subsets are homogeneous. So feel the difference compared to the standard graph regularity. You don't say it's not only that the almost all k tuples are regular and behave nicely, but it's actually that almost all of them are perfect. Either you have all the hyper edges or you have none. So the first result in this direction was obtained by these folks whom I already mentioned. And in fact, what they set out to study was not semi-algebraic hypergraphs, but rather what they called geometric expanders. So they looked for higher dimensional variants of expanders. What they have shown is that once you have a ky semi-algebraic relation of bounded description complexity, and you have a finite set of points. So again, we have, with respect to this relation, you have an epsilon regular partition in this very strong sense that was just stated. And originally its size was enormous, and it was subsequently improved to polynomial by Volksbach and Suk. So they obtained what was called polynomial regularity lemma. And the result was also somewhat constructive, so they obtained this bound, but when we are looking at these exponents, they were not very specific, and they depend on stuff like degrees in the polynomial inequalities, and generally they were not worked out explicitly. So there are some interesting applications of these results. Let me mention property testing in semi-algebraic hypergraphs. As I mentioned, so there was also a very interesting relation to the basic result in geometric Ramsey theory known as same-time lemma. So if you have n point sets, suppose m is fixed, then you have large subsets of so that if you look at all the sequences of one point from each subset, then your order type stays invariant. And it is used to establish nice bounds for variants of Herder-Sekerash theorem. And so you can use regularity results for proving such statements, and much, much more. And basically you can replace order types, having same order type with satisfying or some sort of some semi-algebraic relation. And I also direct you to look into the recent bound by Buch and Vasilevsky for same type lemma, which technically proved partial inspiration for this paper. So there is, before we dive into regularity, let me also mention the result that I have presented in my previous visit using semi-algebraic density for improving bounds for K-sets and point selections. So this new result, we finally obtain an efficient regularity lemma, a really efficient regularity lemma for semi-algebraic hypergraphs. So, the size of the partition is basically 1 over epsilon to the power of d plus 1. There is this delta which can be chosen arbitrarily small. And it can be constructed in almost linear time. Linear if you allow epsilon to be fixed. It's also, you can get rid of this delta if you assume certain general variant of general position for the hypergraph. So for most applications, unless you are working with incidences and such, but otherwise this delta does not come into play. But there is an added cost in the running time. And if you if you also don't insist that the partition is that the partition is equitable, if you trade equitability for some a reasonable assumption on the cardinalities of the subsets, as you can see, that they should be at most of size epsilon to the dn and such, then of course you can get rid of 1 in the exponent. So d plus 1, the 1 comes from the equitability. And but what is truly interesting, and I think it will have important implications for a variety of geometric problems, is that the partition, unlike its predecessors, it does not depend on the underlying semi-algebraic relation. As long as you have fixed a certain bound on the number of polynomial inequalities and on the degree of those inequalities. So you don't care what is the relation. It can, it's good for any number of semi-algebraic relations. And before we proceed, let me also mention that after this result has been made public, Theodore and you mentioned to get rid of delta in the exponent. But to the best of my knowledge, the proof is not very constructive, and it's very uses more intricate algebraic tools. So if you are speaking of constructions, let me also mention that okay, you can look at this as a data structure problems. I hope mathematicians here are not scared. So you can say, I can tell I don't know this semi-algebraic relation. I just go and partition my point set, and okay, this gives a nice data structure for finding a set whenever you have the query semi-algebraic relation, like you can go and quickly report a small size superset of k tuples or that are not that include all the such k tuples that are not homogeneous. It's hard to report the exact k tuple that are not homogeneous because we can go fall into some hardness and such stuff, but you can easily report a small size superset of such k tuples. A byproduct of this new regularity result is, of course, an algorithmically efficient variant of the density lemma. So combinatorially, it's a bit weaker than what I have established in the previous paper, but algorithmically, it returns a large size k clip really fast. Because as a rule, you can always, okay, it's not division, we should multiply here. But whenever, if you, any regularity result of this kind implies a density result automatically, if you give it a thought. So what are the ingredients? One very non-surprising ingredient is the polynomial partition of good and Katz, which is familiar to many of those present here. Another, but the one ingredient which is less trivial is lifting the polynomial, partitioning polynomial into dimension d times k in order to analyze k tuples of subsets that are possibly not homogeneous. And this is actually inspired by the work of Buch and Vasilevsky, who studied same type lemma. And we also use Baron-Dazou bound on the complexity of cells in the polynomial partition that intersect a given hypersurface of small degree. So, yes, I have how much?
I guess it's 25 minutes.
Huh?
It's what, 25 minutes.
Ah, till be
You
fine.
don't have to use them all.
Okay, so in 2010, Gut and Katz obtained a normal sharp bound for the distant distance, average distant distance problem using this nice observation that whenever you have an endpoint set in the Euclidean D space, you can have a polynomial of degree of order r to the 1 over d whose zero set subdivides whose zero surface subdivides the ambient Euclidean space into connected cells so that each cell contains at most n over r points. So I'm going to give us a sketch of the result, and after that I will of the proof. It is actually a very simple argument, and then I will show how to adapt this argument. So the assumption we are going to make is that one can apply a generic perturbation to your point set in your for which you seek an epsilon regular subdivision. You can apply a generic perturbation that does not disrupt the k-wise relation over all the k doubles. So if you consider this, if you let me make this assumption, it becomes a one-page argument. If you also don't care about the construction. So you also, the second thing, it's quite a step which is quite standard, that let's ignore equitability. Because you can first subdivide, obtain a similar partition with every in which equitability is relaxed and replaced by the assumption that the parts are not too large. And then from there, you subdivide the parts a bit again, and you make one more round, and the cardinality of the partition grows by a factor of 1 over epsilon. So this is something quite elementary. So we are going to see an almost epsilon regular partition of this kind. And so let's take the R partition in polynomial, where, not surprisingly, R is going to be 1 over epsilon to the d. And of course, the partition in polynomial, its degree is 1 over epsilon, order 1 over epsilon. So you have 1 order of 1 over epsilon to the d connected cells into which the zero set of the partition in polynomial subdivides the ambient space. So your partition, for your partition, you just, for each cell, you pick a subset of points in that cell. There is also a slight problem. You may ask what of the points which actually fall on the zero surface for which the polynomial g attains value 0. But because we made a certain genericity assumption, we applied a generic perturbation. The number of such points is going to be rather small, at most order of 1 over epsilon to the d, so they can be set aside or something. So how do we analyze the number of subsets or k tuples of subset so that are possibly not homogeneous with respect to some semi-algebraic relation, which, by the way, we haven't used in any way so far. We just took a polynomial partition and that's it. So how do you analyze these k tuples? And of course, the trick is to go into dimension d times k, where the semi-algebraic relation where the k tuples of points actually live. So let me explain how you take the d-variate polynomial and you get d times k variate polynomial. You just in dimension d times k, you have k d tuples of coordinates. So you apply the original polynomial g separately to each d tuple of coordinate. You take the product and you got your polynomial.
So that kind of reminds us of the Vernessa map that's used to originally get a polynomial partitioning.
Who?
So to originally produce a polynomial partitioning or prove that it exists, you go to a similar type thing, the Vernessa map.
Yeah.
But here you do something slightly different. You go to the same. Yeah, okay.
That's actually inspired by Buchert Vasilevsky, but the result was more limited. And among other things, they did not think of it in terms of regularity and using Bazoo and taking your relation. And they also did something more parametric and some to not to use Baron Bazoo. So anyhow, you take this polynomial, you obtain this polynomial in dimension d times k. So you want to answer the question how many k tuples are not regular, are not homogeneous, and you notice that k tuples of cells in the original partition by by the polynomial g in the d space correspond to cells in the partitioning of the d times k dimensional space by this polynomial that we just looked up. So, and furthermore, if this partition, so if you have a k tuple of subsets which is not homogeneous, then the respective cell in the product space you obtain by taking the Cartesian product of the cells inscribed in cells of this part. This cell must cross at least one zero surface of the polynomials which determine your semi-algebraic relation, because somehow the sign must flip for at least one of the inequalities. But according to Baron Bazoo, the number of such cells is at most the degree of g to the power of d minus 1, right? Which is at most order of 1 over epsilon to the d minus 1, and you get an immediate bound on the number of possibly non-homogeneous k-tuples of subsets. But what did we shave under the carpet? All the usual stuff that always gets shaved under the carpet. You have points that live in the zero set, and assuming generic perturbation was too generous thing to do. So you have under perturbation, you have that many points, but otherwise, who knows? And it's a big issue, especially if you look at semi-algebraic relations that come from incidence geometry. And a related question is that if you take your partitioning polynomial, if you take your R depends on epsilon. And the best known construction of this polynomial, it runs in this time, so your running time is maybe quite considerable. It adds a certain unwanted term, right, to the construction time. Currently dealing with partitioning polynomials is not very efficient. So the idea is to get around both problems simultaneously. We want to deal only with partitioning polynomials that have fixed degree. We want only constant degree partitioning polynomials. So this solves the algorithmic problem of constructing them. And in fact, it also solves other problems. Because, so our approach is to construct a sequence of increasingly refined, almost refined subpartitions of the underlying point set. The cardinal in each step, whenever unless your part is already small, you seek to further reduce it by a factor of t, where t is a significant constant.
Computationally, how do you achieve that perturbation?
I will tell in the next slide. And you keep watch after the measure of the irregularity of the partition of the intermediate partition, until this measure becomes satisfactory. But the idea is that in each round it falls by roughly this factor, t to the power of 1 over d. So you can guess where the bound comes from. And the question how you subdivide the part in an intermediate partition, how do you subdivide the certain part and keep it into the subsequent partition? So actually, this step is, though it's a mostly combinatorial paper, but this particular step is using polynomials of bounded degree is inspired by a paper by Agarwal, Matushik, and Sharir, who worked on semi-algebraic range search. So it's interesting because they managed to, for various efficiency reasons, they wanted to keep the polynomial degrees small. And they also had to deal with point sets which reside in hypersurfaces and even varieties of even smaller ambient dimensionality. And they did both of it with success. And so it's important that for in our intermediate partition, every subset is kind of enclosed in a semi-algebraic set of certain dimensionality. And we construct the partition within the proper dimension by projecting it into proper lower dimensional Euclidean space and apply Newton cuts there. So, and the real, I'll omit the details of this somewhat intricate analysis because one big challenge is how do we apply the product trick possibly for point sets of different intrinsic dimensionality, and it does not work right away as stated. So one needs great care. And also for this, this is one of the reasons while when I said that the sizes of the set, the cardinalities of the sets in each sub refinement, they decrease by a factor of t, I have been lying. Because sometimes when they fall into lower dimensional hypersurface, we don't refine them further, we just relegate them to the following step. But this can happen for a single point only, what, d times, so we can live with that with some amortized analysis. So, but so let's just say that dealing with lower dimension points and lower dimensional hypersurfaces and intersections of such hypersurfaces, it adds bulk to the description. But we gain algorithmically from the fact that the polynomials have constant integration.